The first property of functions that we're going to go over that you'll hear about over and over again is domain and range. We've been talking about domain and range since the beginning of time, it feels like. Domain is the x values, range is the y values. And a function is any relation that puts a set of domains to a set of ranges, aka the x's go to the y's and the x's cannot repeat. We also know that if something is a function, it will pass the vertical line test. Do these sound like things we've known before? Okay, great. So I'm not going to spend forever on them. You can do domain and range for coordinate points. You can do domain and range for graphs. And then we're going to learn how to do it analytically or algebraically from just looking at the equation itself. But before we get there, let's look at these examples. If I give you this set of coordinate points and ask you for the domain is really just the set of values. I personally like putting them in number order, but it is not required. I just like putting them in number order because that list looks better that way. So it's just all of the x values from the coordinates. And the range is all of the y values from the coordinates. Again, I like putting them in number order because I like things to be in order. It is not required that it gets in number order. It just looks nicer. And then we can decide if this relation is a function. And all we have to do is decide if all of the x's go to individual y's, aka if any of the x's repeat, it is not a function. So is this one a function? Yeah, it's a function. And it's a function again because none of the x values in the domain repeated. Same thing for the other one. We have 4 coordinates. We can still write the domain of said coordinates. Let me move the mouse off the screen because that's annoying. Now with this domain, you might notice right away that this is kind of interesting. Do I need to put the 4 in this domain twice? No. Once it's on the list, it's on the list. It's like if you were making a grocery list and you're like, I need to get apples and apples. That's annoying. Apples is already on your list. We don't have to list it twice. And with the range, again, there's a repeating -3. That's fine. We don't have to list it twice. And again, you don't have to put them in number order. I just like putting them from least to greatest because I think it's more organized in your list. Now, is this one a function? No. Why is it not a function? Because of the repeating x's. Do we care if the y's repeat? It can repeat all that it wants. In fact, that's called a constant function if it repeats every single time. This is not a function, though, because the x values repeat with different y values. Okay, we've done domain and range for a long time now. It should be getting a little bit easier, especially from these sort of representations. Now, I know a lot of people struggle with domain and range, especially when it comes from a graph. And this graph looks kind of ugly, mostly because the axi didn't print bolder for you. So if you want to bold them in, they're right here. That just honestly makes it easier to see. It just didn't print very well. Okay. All we're trying to do is describe where the graph shows up on the x-axis and the y-axis. If we're looking at this circle, we'd say, oh, well, it shows up from this point all the way to this point. And those are values on this x-axis. That's from the value of -4 to 4. For a continuous function, I don't just list out the numbers, though. I'm going to list this out in interval notation, which means I'm going to say that the domain starts at which value? What number does it start at on the left? -4 with a bracket. Why is it a bracket instead of a parenthesis? Because it's a closed circle. The function exists there. There's no hole. And where does it end at? 4. So the domain for this circle is between -4 and 4 inclusive, which we have represented in that domain. The range is describing the graph from lowest to highest, bottom to top. It's the y values from least to greatest, which is why it's bottom to top. This graph shows up basically on that part of the y-axis, right? There's nothing above or below it. So we're showing up again from -4 to 4, this time on the y-axis, because that's -4, and that's 4. We're using the bracket instead of the parentheses because it's a closed circle. The function actually exists at those points.
Why is it not -6 instead of -4?
-6? Did I count wrong?
Yeah, because the lowest value.
Well, if this is 0,
Oh, am I worried
1,
about
2, 3,
I thought
4.
A and C were connected. That's why.
Oh, yeah, no.
Oh.
They're two separate examples.
Oh, okay.
She was thought these two were connected. No. These are two separate examples. Is that what you're saying?
Yeah.
Part A, part C. Yeah, sorry. Okay, and if we look at this last function, which is going to be more like what we actually deal with in this class. First of all, again, the axes did not print very well. If you want to add your like axis arrows so you know where you're looking, start counting numbers. They're here. Didn't print very well. And if you want to add yourself some arrows to the bottom of this graph, just so you know it doesn't stop there. Might be more annotations that are helpful. Again, I know it printed kind of badly. So we, again, want to check out where this graph exists on the x-axis. Does it ever have a stopping point on the left? No. What does this arrow mean? Keeps going for forever towards negative infinity, this direction. Slowly this direction, but that direction nonetheless. What's happening on the right side? Same thing. It's keeping going out just a little bit. So the further and further it goes out, that means the domain is all real numbers. So you can either use from negative infinity to infinity for interval notation, or the shorthand, if it doesn't require interval notation in the question, for all real numbers is the fun and funky looking R. It's the mathematical symbol for all real numbers. The range, though, is a bit different. Those arrows are headed down to negative infinity. So we're going to begin our range at negative infinity, but it does have this stopping point up here on the y-axis. The graph has a maximum value. That maximum value is 4, and the graph exists at that point, so we're going to use a bracket. So all domain and range is describing visually where the graph shows up. Like if I were to ask you, where should I put this graph on this piece of paper? The circle one, you could be like between -4 and 4, and I'd be like, great, I know where to put it. That's what domain and range is. But we're going to learn how to do this without having a graph and without having to do any of that, especially its domain. That's going to be one of the major struggles of class, is talking about the domain of different types of functions. So for literally almost all functions that we'll study in this class, most of the common functions, the domain is all real numbers. Like pretty much that's a good solid answer to get 90% of the questions correct about domain. There are 3 functions that we're going to deal with in this class that have restricted domains. So basically aren't all real numbers. And those are the only 3 that you have to worry about. Otherwise, you should know the answer is all real numbers. For square root functions look like this, right? And you have this stuff inside. It's called a radicand. I don't know if you've ever heard that word before, but the stuff underneath the square root is called a radicand. And the restriction of a square root function is that the radicand has to be greater than or equal to 0. Because you can't take the square root of a negative number unless you get into imaginary. And we're not doing that with functions because ew. Okay, so the radicand has to be greater than, I totally put that symbol backwards, that's embarrassing, greater than or equal to 0. Okay. Rational functions are the next type of function that have a restriction on them. Rational functions are fraction functions, so they have a denominator. There might be a bunch of stuff in the numerator, but if there is a denominator, then you have to know that the denominator cannot be equal to 0. That's the restriction on its domain. Whatever the denominator is, can't be 0 because you can't divide by 0. Bless you. Logarithmic functions are the third type of function that have a very specific domain. So any logarithm, including your natural log, has what's called an argument, which is like the stuff in the parentheses for the log. A lot of times it's just a number, but sometimes it will be like an expression of sorts. That's called the argument, but it's the stuff in the parentheses. The argument of a logarithmic function has to be greater than 0. It cannot even be equal to 0 because you can't take the log of 0. So if your function is a square root, a rational, or a logarithm, we have to actually do work to talk about the domain. If it's literally anything else, you can say all real numbers and be done. Okay? So So if we look at the first example, again, we're going to do all this without a calculator, meaning we're not graphing it to see what it looks like. We're just going to be able to do this algebraically. That first function, a, what type of function is it? Don't think too hard. What is, when it's squared, what is it called? Starts with a Q. It's a parabola, a quadratic. Correct. That's a polynomial function. Guys, any polynomial function should be our easy answer. What is the domain of any polynomial function? All real numbers from negative infinity to infinity. Done. I don't even have to do work. Quadratics and polynomials, their domain is all real numbers. There's not going to really be anything different. Their range is going to be different from polynomial to polynomial, but their domain is all real numbers. What kind of function is b? Rational. Looks like a fraction. Rational, fractional. Okay, right? So there is a restriction on this domain. The restriction is that the denominator cannot be equal to 0. Now we want to solve that restriction for x. So if I isolate the x, I would just subtract 3 to both sides. This is going to be x does not equal negative 3. Now that means if I were to draw on this number line my domain, here's negative 3, and I just can't include negative 3. Said nothing else about any other number except that it just can't be negative 3, which means all of this is okay except for negative 3 in my domain. So to answer the question, you would say, okay, the domain goes from negative infinity to negative 3. We pick up our pencil. We put our pencil right back down after negative 3, and we finish at infinity on either side of this number line. Because it would be all real numbers, which is that negative infinity to infinity, except that it just can't be negative 3. So we have to talk about that in our domain. Okay, do we see the difference in how we answered A and B? Okay, let's flip on to the back side. We've got a few more examples of this type of question here, where we're just trying to determine what the domain is. Only domain here. Number C is what type of function? Logarithmic. I know it's on the other side, so I'm sorry, you might have to flip back. What's the restriction for a logarithmic function? What, the argument, right? That's this stuff right here inside the parentheses. So x minus 5 has to be greater than 0 for this function to work. Quick solve for x. So nice, it's so easy. Plus 5 on both sides. That means x has to be greater than 5. On my number line, what that would look like is here's 5, open circle, and my domain is just where it's greater than 5. Can we write that in interval notation? Yeah, what would go first? Parentheses or bracket? Parentheses, because it's open. It's an open circle at 5, so parentheses 5, comma, infinity. That's it. Because it's only got one subinterval that I've colored in on my number line, so I only need to answer that one subinterval. Let's look at D. What type of function is D? A square root. What's the restriction on that square root one? Yeah, the radicand, which is the stuff underneath the square root. A less fancy way to say it. The stuff underneath the square root has to be greater than or equal to 0. We quick solve for x. I'll do this one in 2 steps just because I want to make sure we remember that second step. So we add 3 to both sides. And what would we divide by here? And when you divide by a negative number, what do you have to do in inequalities? Yeah, switch the sign. Don't forget about that. Just goes from being greater than to less than if you multiply or divide by a negative. So this number line, for its domain, has a number negative 3. Opened or closed circle? Closed. And we're going less than that. I guess I should color it with the same colors. So we can talk about its domain. That arrow is going off to the negative side, so that's from negative infinity all the way to negative 3, but then including negative 3, because it can actually be equal to it, because that thing can actually be 0. Two more finding domains. We have E. What type of function is E? Starts with an R. Rational. I always want to say fractional, so if you accidentally say that, I get what you mean. It's called a rational function. Okay? What is the restriction on rational functions? What cannot equal to 0? The denominator. Great. So we need to know when this is equal to 0 so that we can say except for those. So we set x squared minus 6x plus 8 equal to 0, and we need to solve. How do we solve something like that?
Wait, isn't it cannot be equal to 0?
Oh, you're so right. Thank you. Cannot be equal to 0. How do we solve a quadratic? Factor it. You could use the quadratic equation. You could complete the square. I'm going to factor. Now we set up our guess and check factors. X's go in the front, and I'm looking for factors of 8 that would end up adding to negative 6. Factors of 8 are 1 and 8 and 2 and 6. You can kind of see where your brain's going, probably to 2 and 6, or 2 and 4, because that'll make negative 6 if you add them together. Which means zero product property tells me that I can still do this little thing where we separate them, where it can't be the first one and it can't be the second one equal to 0. So X has two restrictions. It can't be 2 and it can't be 4. My number line would have 2 numbers on it this time with big old gaps, but literally everything else is okay. All the rest of this is fine. I just can't use 2 and I can't use 4. Take a second to see if you can write that what words am I looking for? Interval to describe this domain. What might be helpful for you if you're pausing on this and just staring at it, whenever you have your number line, you may also want to write in negative infinity next to the arrow and positive infinity next to the other arrow. Because if you're coloring in the number line and it's heading towards one of those infinities, that should be a part of your interval. The interval that describes this domain is from negative infinity to 2, from 2 to 4, and from, I'll stay on the same line, and from 4 to infinity. So literally everything except for the numbers 2s and 4s, because I had to pick up my pencil at that point, because that's where the denominator would be equal to 0. And every time there is an interval, you just connect it with the little u. It's the word and. Okay, so you know how in math class, the teacher's like, yeah, it's not so bad, right? And you're like, not so bad. And then they give you the hardest problem to try on your own. I'm going to do that now. So F is for you. There is 2 problems with F. I want you to try to do both problems at the same time. See what you come up with for the interval. Write it in pencil in case it's wrong, and we'll just erase it and try again. You guys got it. You've got people near you who you can talk with too. The x plus 7, since it's part of the radical, it's the radicand, has to be greater than or equal to 0, and the entire denominator cannot equal 0. Both of these we can solve pretty quickly. So we would subtract 7 from both sides. We'd factor this. It factors out to x plus 3, x minus 4, which means x plus 3 can't be 0, and x minus 4 cannot be 0. So x can't be negative 3, and x can't be 4. So we have all of these things happening. We have x has to be greater than or equal to negative 7, but it can't be negative 3, and it can't be 4. So when we draw our number line, we take all of that into account at the same time. Here's negative 7, here's negative 3, here's 4. We have holes at negative 3 and 4 because it can't equal to those. We have a closed circle on negative 7 because it can be equal to that. And then it's everything that's greater, just jumping right over -3 and 4. So when there's multiple restrictions from different parts of the function, you just include them all on your number line so that you can write the domain correctly. The domain here would start at -7, stop at 3 for a hot second, sorry, -3, pick back up at -3 and go to 4, pick back up at 4 and go off to infinity.
So I was somewhat right.
Okay, take a second to digest and let's ask some questions. Okay, so the second concept about a function that we can talk about is the function's continuity. Now, we've talked about continuity before in math class, comparing it to a discrete versus continuous function. That's different. We're not really talking about continuity in that space, like it's not just because they're connected lines that they're continuous. There is actually a definition for continuous functions beyond just comparing it to discrete. But the way that we're going to talk about is it will be continuous if you can draw the function without ever lifting your pencil, a very technical definition here. So we're going to talk about different types of discontinuities because not all functions are continuous. This first graph is not continuous. Do you see that little hole in it? That's not a typo. This is a discontinuous, or I always spell this word wrong. I don't get it because it's not a hard word to spell. Discontinuous. Okay, I think I got it. This is a discontinuous function because it has what's called a removable discontinuity. I like to call them holes. You can do the same. But it's a removable discontinuity. Basically, I can fix it with a pencil. Like I could plug the point back in there and it would be, it's like I just removed it. So it's called a removable discontinuity. The second, oh, sorry, yes. Okay. The second example is also discontinuous. Does anyone remember the name of that thing that's happening in the middle of the graph? Close. We did draw those dashed. Oh, I heard it. What is the asymptote? This is a vertical asymptote. It is a non-removable because I can't plug it with a pencil. That graph jumps from positive infinity to negative infinity. And is it okay if I just do VA for vertical asymptote? Is everyone okay with that? You can also make that shortcut too because those are both long words. Vertical asymptote.
Oh, that's what VA means?
Vertical asymptote. HA is horizontal asymptote, if you ever see that. The next one, do y'all think that one is continuous? No, that's also a different type of discontinuity. It is not a vertical asymptote because you don't have the lines and it's not going off to infinity one way and negative infinity the other. This is a non-removable because I cannot plug it with a pencil, and it's just called a jump. You'll see those happening a lot with piecewise functions, that they have these jumps.
What functions?
Piecewise.
Huh?
I'll teach you about them in like 3 class periods. Don't stress about it yet. Now this last function, do you think it's continuous?
Yeah.
Good, because it is. As I drew, if I were to be drawing or graphing this, I never would have to pick up my pencil for a hole, a vertical asymptote, or any sort of jump. It's a continuous function. So continuity, not in the sense discrete versus continuous, but like, is it all connected together with no jumps? If yes, it's continuous. We feel good about that topic? I like that one. That one's quick. Okay. We have continuity. The third thing we can talk about a function is called increasing and decreasing intervals, or the parts of the function that are increasing or decreasing. If you don't have multiple colored pencils, grab some of the highlighters from the box. I think there's like 2 or 3 colors, because this is best explained in color. The graph on the right is decreasing on the interval from -1 to 0. Makes sense. That part is the decreasing interval. Now, where did we get the 1 and the 0 from, you may ask? That's because that's the domain, or the part of the x-axis where that little red section is showing up. The graph, if we were reading it like a normal graph, we'd be counting down. The slope would be negative. We'd be walking down. All of those things talk about decreasing parts of functions. The next section is called constant. That's not a highlighter. A constant part of the function, because it's just flat. That makes sense, but where did we get the numbers 0 and 2? We got them because this is the interval on the x-axis where the graph is flat. Okay, that little section right there, from 0 to 2. The third type of, wow, I just lost my whole train of thought. Graphs can also be increasing, obviously, when they go up, like from 2 to 3. Where do we get the 2 and 3 from? From the x-axis. That's the domain interval where the graph is going uphill or upwards. Now this is very confusing because you're not following the arrows necessarily, and you're going to see why I say that on our next example. You're like as if you were walking across the graph. Am I going down? Am I going flat? Am I going up? Right, that's what you're going to be looking at for these functions to decide where it's increasing, decreasing, or constant. Sounds like duh, but I promise you this next example, you'll look at it and be like, I got this, and they'll be like, oh, wait, huh, what? And I'll re-explain what I just said because it will make sense. Okay, I'll give you time to color, and we'll look on the back side. Okay, we need to decide on example 4 what intervals the function is increasing, decreasing, or constant. So first things first, let's go increasing. We just need to find where this graph is going up. Do you agree that this section is going up? Great. This section is also going up. That's a true fact. That section is also increasing. And here's where you're going to get confused. You're like, Ms. Quigley, that arrow's going down though. I know. But if I were walking across this graph, I'd be walking uphill, right? I'd jump. But wouldn't I still be walking uphill? If you're still reading the graph from left to right, it's still an increasing section. Okay, so this graph is increasing. That's not right there. This graph is increasing from, what is that? From 2 to infinity. Oh, that's not infinity. Where does it stop? This is 4 to 4. My bad. There's no arrow at the end there. So that little section, though it looks confusing, is all increasing because at every point I'd be walking uphill. Yes, there's a giant jump. That's okay.
So is it just increasing?
I've got a hand. Is it just increasing? What do you mean?
Like, because there's that other line right there where it's like looking like it's decreasing. The one that's going from 0 to 1.
Right. Oh, so this section right here, I didn't point at it. Here?
Yeah.
That is the decreasing section.
So do you not worry about that? Or?
Well, that's just part 2. We are
Oh.
decreasing from 0 to 1. I saw another hand. Did you have a question or a comment? Oh my gosh. I told y'all so wrong right now. Nope. I did. Guess what's happening right here?
The asymptote.
The asymptote. We got to talk about the asymptote. So we're gonna hold off on saying 4 for right now. We're gonna say it goes to 3. Pick up your pencil at 3 and then go to 4. I'm so sorry. I forgot about the asymptote there. Because there's a gap right there where it's not increasing or decreasing. There's like a little. So sorry. My summer brain is gonna leave me soon. I promise you. The last little bit we have is the constant section. This little piece right here is constant because it's flat. And that's the interval from 1 to 2. Now, question. Why did I put that little parentheses here? Because it's an open circle. Oh my gosh.
Did you forget something again?
That should be a whole parentheses. That should be a whole parentheses. Oh my gosh, I'm so embarrassed. Well, you can tell I'm human. Ta-da. Yeah, if you catch my errors, please say something so I don't look silly going back and like erasing half a problem. Glad I'm recording this one too so everybody on the YouTubes can see my mistakes. Sorry, YouTube. Okay, now that I've thoroughly confused you, Increasing is the sections of the graph where the graph is going up, looking for holes at the same time, like I forgot to just now. Decreasing is the sections of the graph where the graph is going down. Constants are the sections of the graph where it's flat. Do we feel okay about that? For the maybe?
For the most part.
Okay, do we have questions about that? Boundedness and absolute and local extrema are something you've probably either heard of before or will be like, yeah, that makes sense. Boundedness talks about whether the graph has an absolute highest, absolute lowest, or absolute highest and lowest points. What I mean by that is, let's say a graph looks like this, a good old-fashioned quadratic. Do you see how there is a lowest point, right? It's bounded below. There is a lowest value. That's called bounded below. Let's say we have something bounded above, like a good old-fashioned negative parabola. It has a highest point. It has a boundary on the top. So bounded below, bounded above. So bounded graphs have both a highest and a lowest point. A circle would work, or the sine function, which is a sine wave, looks something like this. You don't have to know much about it yet. I will teach you later. It has both a highest, I drew that really bad, and a lowest point. Pretend that's all within there. So it would be like something that oscillates, which means it goes back and forth. That's a bounded function.
So it's basically just both. There's both highs and lows.
Both highs and lows. And then there's like the option of unbounded, which means there is no highest, there is no lowest point.
Just a constant, like y?
So like, that's a good question. If you had just like the cubic function, you see how the arrows go off in both directions? That is an unbounded graph. There's no absolute highest, absolute lowest point besides infinities.
Oh, because they keep going forever. Okay.
Yeah, it has local highs, maxes, and mins, but no absolute maxes and mins.
Like no official ones?
Right, essentially. Higher than literally all the other points, or lower than literally all the other points. We get bounded, has a top, has a bottom, has both top and bottom, stuff like that. Okay, the last concept kind of goes with boundedness is absolute and local extrema. Extrema is just a word that's like plural, and it talks about both maxes and mins. You would have probably only called them maximums and minimums to this point. Extrema is just like the lazy way to talk about all of them because they're the extreme values. A local or relative extrema is when the y values are bigger than everything surrounding it, but not necessarily the highest or the lowest. You have to have a left side and a right side of this point to be able to talk about relative extremas. So if it's at the end of a graph and you don't know what's happening on the left or right side of that point, it is not a relative extrema because you don't know if it's bigger than the stuff on the left or the right side. Absolute extrema are the absolute biggest or smallest. They can be on the ending points because you know they're bigger or smaller than everything else that is showing. So let's just label all of these points on this graph as whether they are absolute or local maximums and minimums. Okay, A is this one right here. This point, is it a maximum or a minimum? Is it the lowest it goes? Yes, so it is called an absolute minimum. Don't let it fool you. B is not next. B is all the way over here. I don't know why it's labeled this way, but it is. Now, is that the highest or the lowest? Neither. We cannot decide if it's a relative max or min because I don't know what's happening over here. It could go like this and make it a minimum. It could go like this and make it not that at all. So we just say neither. If it's an absolute, if it was the highest, you could say absolute maximum, but it's not. It's just kind of like chilling in the middle. C is right here. That is a maximum, but is it the highest that it goes? No, so we're just going to call it a local maximum. Because it's not the highest or the lowest, it is just a high or low point. Like it's higher than all of these values and higher than all of these values surrounding it.
So then would D be a local minimum?
It would be. So D right here is a local minimum because it's a low point, but not the lowest. We already talked about the lowest. There can only be one per function. And then E, absolute highest. So yeah, absolute maximum. So absolutes can be on ends. I know I kind of ran out of space there. But the locals, if they're on an end, they're neither. You can't tell me. Yes. Yes.